Good morning, I'm Athanasios Lambrou. I'm a lieutenant junior grade in the Hellenic Navy, and I'm going to present you the paper Capital Budgeting Techniques in Energy Systems Application in Marine Industry. I would like to thank all the co-authors who worked in order to write this paper. The agenda of the presentation is shown at the current slide. The previous 2 days we saw many systems regarding energy in ships, which actually can increase the efficiency and reduce the emissions. But what about their techno-economic evaluation? And today, in this presentation, we are going to show some tools that managers can use in order to evaluate such systems. So, firstly, we are going to talk about 4 evaluation techniques. The next topic we are going to talk about is a case study, which is the installation of an after-treatment system in a ship. And at the end, all the findings of the paper will be quoted. Firstly, payback period is also known as the capital recovery period, and actually it is the time needed in order to get all the invested money back. For example, if somebody invests today 5,000 euro in something, and he's promised 2,500 euro 1 year from now, and another 2,500 euro 2 years from now, the payback period would be 2 years. The discounted payback period is quite similar with payback period, with the only difference that we discount all the future cash flows into present, both incomes and outcomes. The rate that we discount the cash flows into present is the rate needed from the owner to compensate for the time value of money. Discounted or not, payback period is preferred to be shorter. This is the rule that we follow when we decide with these 2 methods. Investments with front-loaded cash flows have a clear advantage in these 2 methods because cash flows that come after the payback period do not affect the outcome. Although being the simplest of all the methods, they give a rough measure of the liquidity of the investment, as well as they give a measure of the underlying risk of the investment. For instance, in industries where equipment becomes obsolete quite rapidly, we want to get our money quickly back, and investments with earlier cash flows have a clear advantage. Finally, these 2 methods should only be used as an initial screen of investment projects, and of course, decisions should not be taken with evidence from these 2 methods only. The next evaluation technique that we are going to discuss is net present value. Net present value is the present value of all expected cash flows, both incomes and outcomes, both discounted into present. In the current slide, we can see a tangible example of discounting a cash flow into present, as well as the mathematical type from which we can calculate net present value. In the mathematical type, T means a period reflects a period of time, CF is cash flows, incomes and outcomes, R is the inflation rate or cost of capital, and finally N, it is the periods that comprise the economic life of the investment. The decision rule followed when we are using this technique is quite simple and clear as soon as all the required calculations have been made. When net present value is positive, this means that we should accept the project because the investment is going to increase the value of the firm. On the other hand, when net present value is negative, we should reject the project because the value of the firm will be reduced when taking the investment. Finally, when net present value is equal to 0, we should be indifferent about accepting or rejecting the project, and we should evaluate the investment, the project, with other techniques. When there are 2 or more competing projects, we should accept the project with the higher or highest net present value. Furthermore, net present value method takes into consideration 3 basic factors that every manager should have in mind. they are interest lost, the factor of the risk, and inflation rate. Firstly, the interest lost is a major factor because we should take into consideration the fact that the return from investing in something must give higher returns than just, for example, investing in a bank. Additionally, risk factor is something that is closely related to investments because every investment has underlying risks. And finally, inflation rate is a factor that every manager should take into account because our money, our purchasing power reduces over time. A tangible example of the underlying risk is, for example, the action of buying an equipment with the perspective of selling it after a few years after using it has risk because we may not be able to sell the equipment or sell it in a price that lower than the price we expected. This is a risk. This is a risk. We are going to continue with profitability index, which is widely known as the benefit-cost ratio, since it is the ratio of the benefits of an investment to its cost. The mathematical type from which we can calculate profitability index is shown at the slide, and we also have to say that this method can show us how much value will be earned for each fund invested. The decision-making policy regarding to this method is quite simple too. When PI is greater than 1, we should accept the project because this means that we will get as a return more than €1 for every €1 that we invest. So we will accept the project. When PI is smaller than 1, we should reject the project because this will return us less than €1 for every €1 that we invest. Finally, when PI is equal to 1, we should be indifferent about accepting or rejecting the project. And the last method presented is internal rate of return, or IRR. Actually, it's closely related to net present value because we practically try to find the IRR which solves the equation of net present value equals to 0. We can say that this method it may be difficult to calculate the IRR by hand but there are many software packages that can do this with ease. Also, we can try the technique of iteration in order to find IRR when high accuracy is not our primary target. A drawback of the IRR method is the fact that it has difficulty handling projects with unconventional cash flows because outcomes do not exist only at the beginning, at the outset of an investment, but also in its future life. And this may lead to complicated calculations and finally find more than one IRR or even no IRR at all. This would make IRR method difficult to use and unfriendly to the user. Furthermore, IRR could easily lead to wrong decision being made because in every investment we will have a required threshold above which we will accept the project. And after completing the presentation of the 4 evaluation techniques, we are going to move to the case study. The purpose of the study is the calculation of net present value and discounted payback period of a real investment, which is the installation of an after-treatment system called Scrubber in a 38,500 deadweight tonnage tanker. We prefer these 2 evaluation techniques because they are friendly to the user, because they do not need complicated calculations, as well as they do not give misleading results. Regarding the system, Scrubber uses fresh water to which sodium hydroxide is added for the neutralization of sulfur oxides emissions in order to meet IMO's legislations for inside and outside ECAs, which are emission control areas. We prefer to evaluate this specific system among all the after-treatment systems because it can virtually reduce the emission of SOx virtually up to 0, as well as it can reduce all the reduce the emissions of particulate matters and nitric oxides quite significantly. At the current slide, we can see the existing ECAs as well as possible future ECAs. Also, we can see that Mediterranean Sea is a possible future ECA. The two parameters that vary in our scenario is how much time does the ship travel inside an ECA, and the gap between the prices, the two feasible fuels that the ship can use, heavy fuel oil and marine gas oil, low sulfur. We presume that when being in an ECA, the ship is going to use heavy fuel oil with the after-treatment system scrubber instead of using marine gas oil, low sulfur, which appears to be more expensive at the moment. The chart pie that we can see in the presentation shows us the operation profile of the ship as we constructed it. For example, we have presumed that the ship will travel for about 66% of the year, which is 240 days, will remain at harbor idle for about 25%, which is 90 days, and will remain at harbor unloading for 9%, which is actually 35 days in a year. At the current slide, we can see the installation cost needed in order to take down the scrubber system, and we can see the cost of each of the equipment as well as the total cost of the installation. And here we have quoted the consumption table of the specific ship, which can show us the consumptions of the ship for both the two fuels, as well as for each of the situations that the ship will be. We are going to use this data in order to construct the profit function that we will see in this slide. In the profit function, we have two variables. Variable x, which is the ECA activity, and variable g, which is the gap between the two prices, between the prices that the ship can use. It can be easily noted that when x and g grows, so does the profit. It has to be mentioned also that the last year's price gap between the two fuels, heavy fuel oil and marine gas oil, low sulfur, ranged from 250 to 350 US dollars per ton, with the arithmetic mean of all these prices of the last year being 283 US dollars per ton. However, according to studies, this gap will increase in the near future, and maybe it's going to reach up to 600 US dollars per ton. Of course, all these prices may not move as expected, and finally, we have to say that in the profit function there are also two constants, C1 and C2, which were calculated from the consumption table shown in the previous slide. The outcome of the profit function per year is shown in the current slide. We can see, for example, that for ECA of 30% and a gap between the prices of 400 US dollars per ton, this is the purple line, that for a year, a manager is going to earn approximately $1 million in a year from his investment. And the net present value will be calculated by this equation shown in the slide. Furthermore, we have to say that the inflation rate was chosen to remain constant and equal to 2%, as it was the maximum price of the inflation rate over the last year in the United Kingdom. We have chosen to accept the worst case scenario because in any of the circumstances, things may turn to be better. And also we have to say that the installation cost needed to take down the system is paid wholly at the outset of the investment. After performing all the required calculation of the mathematical type given in the previous slide, we will get this figure. We can discern 10 possible scenarios, and of course there are many other scenarios, encouraging and disappointing, that could be depicted, but we couldn't depict it in a single diagram. From these 10 scenarios, some give promising outcomes and some not. The discounted payback period ranges from 5 to 15 years, and this is when the net present value curve tends to be positive. Additionally, some outcomes of net present value are positive and others are negative. The most encouraging of all the cases is for ECA activity of 30% and a gap between the prices of the two fuels, heavy fuel oil and marine gas oil low sulfur, of $450 per ton. However, we should say again that there are also other scenarios that are more encouraging and others more disappointing than those depicted in the previous diagram. For instance, there are ships that travel only inside ECAs. In that situation, the financial analysis, the techno-economic analysis of the investment of the scrubber system would give us a result for example, discounted payback period less than 2 years. So we absolutely would accept the project. Also, we have to mention that we have chosen the worst case scenario regarding the inflation rate, and moreover, the whole capital needed in order to install the system in the ship was paid wholly at the beginning of the investment. Of course, this might not be a realistic scenario because it's more likely to pay for the system in a period of time and not at once. In conclusion, 4 techniques for evaluating long-lived assets were introduced. Except from how each method works and what does it mean, and the mathematical types that describe the method, a brief decision rule was given. Furthermore, we tried to explain practically 2 of the 4 evaluation techniques in a tangible example related to energy in ships. So the case study scenario refers to the installation of an after-treatment system in a ship in order to reduce the sulfur oxides emissions. The ship, after this alternation, would meet IMO's legislation about IMO's restriction in SOx emissions inside and outside ECAs. The outcome of the study shows us that there are so many situations that we should accept the project and others that we should reject the project. So, concluding, we have to say that there are many factors that every management manager should keep in mind, because every investment is closely related to risk, or even better, every investment means risk. And here the presentation has come to an end. Thank you very much for your attention.
Almost every energy saving project has issues with the profile of the ship. If it's on the underwater side, it has to do with your speed. If it's on the HVAC side, it has to do with your location. And so how do you get it for the scrubbers has to do with the same as location. What's the best way to hedge and make a responsible profile? Because depending on how you squeeze the data, you can go for it.
Yeah, and the whole scenario is built with a constant speed of about 15 knots.
So that's fine for the scrubber, but if you're doing a new paint, or if you're doing a dovetail, this all depends on the speed of your ship. So if the ship is changed to a different itinerary, you go from 20 knots to 12 knots, your IRR changes. And the same for your AC upgrades, because if you're in the tropics all the time, when you go to the North Sea, it's going to change.
Yeah, of course.
And the problem I have when I'm doing this is build your profile of how to do it responsibly. Because if your charter changes or your itinerary changes, all of a sudden, profile changes.
If I understand the question,
scope of our specific paper was examining the economic evaluation of the project. The operation profile has been received bibliography, and the operation profile is based on a real situation. I mean, at sea cargo and unloading. On the specific paper, you are absolutely correct that there are also other parameters, but in the specific paper, giving us the appropriate information regarding the cost of the scrubber, which is not easily found. There was no other information regarding the other parameters you correctly mentioned that are involved. So we were not able to evaluate all these factors.
No, I understand that the paper is, if you try to, as models become more complicated, if any of them find any guidance for how to define your model.
Yeah, definitely you are absolutely correct regarding the specific evaluation. There must be also other parameters specific consideration. But the scope of this one was to give only the ability of the manager to decide under the specific circumstances which is the best economical solution.
It's a way of taking into account the alternatives, not just in Lamprou, but stochastic analysis.
Yeah.
It would be much more interesting to see how these numbers would change and how the risk would be inside the evaluation of just
Yes, you are also correct.
It's for the next step. It's the next step.
Mr. Lambrou has cited the procedure that three of the most well-known, let's say, evaluation techniques, which would be more acceptable nowadays in specific programs, let's say, because even the specific are not so acceptable except maybe the